All right, good morning, everybody. How's everyone today? That's a Monday morning response. Good, good, awesome. All right, well, week 6, a bunch of stuff I want to talk about today. I want to talk a little bit about homework 4. I want to go over lab 5 and then introduce homework 5. I want to talk a little bit about the midterm as far as expectations for taking it and turning it in. You can't hear me. All right.
I can.
Yeah. Let me check something over here. Testing. So Zoom says it's coming through. All right. We got 3 icons. So could be a local Zoom issue. All right. Okay, cool. All right, so I want to talk about all that. I want to talk about the midterm as far as procedures and expectations for taking it. And then I want to continue talking about state machines and developing that analysis technique that we started on Wednesday. So anything you want to ask or talk about up front before we start all of that, this would be a great time to ask questions and such. All right. Well, let's talk briefly about homework 4. So this was I got this graded last night. It's going to take me a little longer for the lab, but I'll hopefully get through that today. So question 1 I mentioned was a sort of there's not a strict procedure for doing this kind of question. It's about sort of looking at the circuit, maybe writing some truth tables initially to get an idea for what it does, and then trying to draw some timing diagrams to show somebody the behavior of the circuit. And so if you look at this circuit, let me sketch it out here, and then I'll switch back. So we've got an AND gate, we've got an OR gate with a NOR on the output. We've got a funny inverter going into R. We've got S, and we've got a feedback loop and Y. So something like that. And so if you think about this, for example, if S equals 0, then it doesn't matter what's going into this input of the AND gate, because anything ANDed with 0 is going to give you a 0. And so zeros are nice things to consider with AND gates. Ones are nice to consider with OR gates. So this is a 0, which means this thing is basically an inverter. So if S equals 0, our circuit looks like this. Right, so R goes in here, gets inverted into here. This NOR gate is acting like an inverter. And so Y is basically equal to R. And the feedback from Y has no effect because S is blocking that from coming out of the AND gate. So if S equals 0, then R is equal to Y, or Y is equal to R. If S is equal to 1, then this AND gate is really just a wire, right? If this top line is a 0, the output will be 0. If it's 1, it'll be 1. And so our circuit looks like this. R goes through an inverter, and it goes into a NOR gate. There's Y, and this comes back in. And so if R equals 0, well, let's if R equals 0, then this is a 0 here. This will be a 1 coming in here. The output of the OR will be 1. The output of the NOR will be 0. And so Y will be 0. If R equals 1, then we have a 0 going in here. And this is just a big inverter. So we have an inverter feeding back itself. And so Y will oscillate. So what are some of the behaviors we want to show in a timing diagram? Well, certainly we want to show a case where S equals 1, R equals 1, show that it oscillates. S equals 1, R equals 0, show that Y is equal to 0. And then S equals 0, show that Y follows R. And so our inputs are S and R, our output is Y. So maybe start with, S high and R low, and Y will be low. And then maybe raise R to a 1 while S is 1 and show that it's oscillating. And then drop R back to a 0 and show that Y goes to a 0. And then we can go ahead and we can drop S and show that Y follows R, so if R goes high or low, Y should just match that. And so that might be a sort of typical timing diagram you could draw for this. And it shows, the different modes in which the circuit operates. There's a mode where it's oscillating. There's a mode where the output is following the R input, and there's modes where the output is just low. So something along those lines. And this one I kind of eyeballed, but I did not grade points for this one. But I did grade the others and gave feedback if I saw issues. So this is one of the harder kinds of questions you can encounter, right? Because it's not like, fill in the columns of a truth table where you can follow a set of steps. It depends on the nature of the circuit to know, how you should drive the inputs in order to show some interesting output. And you'll see this in some of your labs, but you've already done this in your labs, right? When you have your traffic control system, how do you demonstrate that it works? So how many different switch settings do you need? And in your final traffic control circuit where you have yellow lights, right, you're going to have sequential behavior like that circuit from question 1, where it's not just enough to say, hey, when all the sensors are 1, this light's green, these lights are red, right? Because if there's no car to the east and there's a car to the south and then a car comes to the east, something different happens from if there's no cars anywhere and then a car comes to the east. Or if there's a car to the east and then it leaves and then another one appears. So thinking about how to sort of show different behaviors of the system is a good exercise there. All right, question 3. This was about setup and hold times. And remember, the idea is that around the clock event, meaning a little before and a little after, your inputs have to be stable, right? So your flip-flop here has an input, right, some sort of excitation input, and it can't change right before or right after the clock tick. And so for question 3U, you're asked to develop a timing diagram for a circuit. So this is a positive going clock. So your clock is doing its thing on the 0 to 1 event, right? So the 3S question was a negative going clock. When the clock drops from 1 to 0, that's when the action happens. But in this question 3U, it's when it changes from 0 to 1. It has a non-zero setup time and a non-zero hold time. And it wants you to show the excitation input for the sequence 10110. So you can usually begin these by just drawing the clock. And the clock we usually don't think a lot about because it's a clock, right? Clocks tick at the constant frequency that they're designed to tick at. And it usually doesn't change. And in good circuit design, we never really mess with the clock. We take it in and we respond to it, but we don't usually, run it through logic or do things to speed it up or slow it down and so on, unless you're overclocking your PC. That's a different story. Thank you. So here's the clock. And we want to input 10110. So there's this forbidden zone. So the clock events are the positive edge. And there's some kind of forbidden zone during which our inputs have to be stable. And so some amount of period of time before and after, everything has to stay put. What we're going to discover this week is during this period of time, that's when all of this random logic in our state machines, that's when they're doing their thing, they're settling in. So this machine we started working with Wednesday, it's during this period between the end of the hold time and the start of the setup time, that's when all this logic is settling. All of the propagation delays and everything are running through, and by the time all of that is stable, right, we should not have hit this forbidden period yet. And then when we get to this critical point before the clock, everything should be fixed. Nothing should be changing. And nothing should change too soon after a clock event. When the clock ticks, the flip-flops will start to update their outputs, and those updates will go through logic and so on. But nothing should change on the inputs of the flip-flops until after a little bit of time has passed. So this is looking at a typical pattern for this particular input, 10110. So the idea is, before this forbidden zone for this first clock tick, our input has to be high. So I'm just going to show it, as starting off its life high. And it cannot change until after that period. Alright, at this point right here, it's got to be low. At this point, it's got to be high. This point has got to be high. This point has got to be low. What it does in between here and here can be anything. So typically, we would come out here a little bit, and at some point, this input would drop. And then somewhere over here, the output might go high. But, it could be that over here the output goes low and then goes high and then goes low and then goes high. That's perfectly legal too. And it could be that over here it stays high for a long time and then drops low for a little bit and then comes low. And there could be glitches, right? But the point of the clock is, during this period when all of the flip-flops are actually paying attention to what's going on, the input is totally stable. So what does the flip-flop see? 1, 0, 1, 1, 0. It's a perfect circuit. So you don't need this. I mean, normally you're just going to draw, high, low, high, high, low. But that would still be a perfectly valid scenario for this circuit. What you don't want to have happen, for example, is dropping the clock right here. That's going to cause your flip-flops to potentially malfunction, because you're violating the hold time in this case. Your input was high when the clock event occurred, but then you dropped it too soon. And you also would not want to do this. Right? Because when the clock ticked, your input was low, and then you raised it a little bit after the clock tick. Well, is it going to see the 0 or the 1? It's probably going to see the 0, but since it's changing during this period, it could become unstable. And these flip-flops can sometimes begin to oscillate. And the oscillation happens because of things like this. Because in some cases it's possible if the clock changes at almost the exact same moment that an input changes, you can create a case where the bits are basically chasing their own tail, and then you get oscillations. So that's what that question was looking at. All right, question 4. And some people came into office hours or lab hours, and we worked through this, and if you approach it the right way, it's not too bad to figure this out. But what's the right way to approach something like this? So we're trying to create a toggle flip-flop out of a D flip-flop. And this solved example, for example, this is something we normally don't do. We don't take the clock and run it through an inverter. The kind of cardinal rule here is don't mess with the clock. But you can, right? And we saw how to do that to make a counter out of T flip-flops last week. But usually we'll avoid doing something like this. So we want to make a T flip-flop out of D flip-flops. So what does a T flip-flop do? It potentially inverts the current output of the flip-flop each time the clock ticks. If you set the T input to 1, you tick the clock, the output will toggle. If it's a 1, it'll go to a 0. If it's a 0, it'll go to a 1. If the T input is 0 and you tick the clock, nothing happens. The output stays where it is. A D flip-flop, on the other hand, just sets the Q output to whatever the D input is. So if D is 0 and you tick the clock, the output's 0. If D is 1 and you tick the clock, the output is 1. And so the question is, how do you take one of these and make one of those? And one way to think about it is break it into cases. Pretend you're writing code, maybe. Let's make an if statement. So if T equals 0, then we want Q plus to be equal to Q. If T equals 1, we want Q plus to be equal to not Q. All right. Well, let's do these in cases. Let's do the case of T equals 0. And the idea is when the clock ticks, we want the output to be the same as what it currently is. Well, what that means is that if the current value of Q is 0, we want the output to be 0. So if Q equals 0, we want the next Q to also be 0. Well, with a D flip-flop, if we want the Q to be 0 after a clock tick, the way we do that is by making the D input equal to 0. And so we want D equal to 0. On the other hand, if Q equals 1, then when we tick the clock, right, T is 0, we want the new value of Q to also be 1. So if Q is 1, we want the next Q equal to 1. And how do we make the Q output of a D flip-flop 1? We set the D input equal to 1. So now we can start making a bit of a truth table. If T is equal to 0, then we want our D input to be 0 if Q is equal to 0 and 1 if Q is equal to 1. So let me do a T and a Q. And let me take all of this wordiness and put it into a truth table. If T is 0 and Q is 0, we want D to be equal to 0. If T is 0 and Q is 1, we want D to be equal to 1. So that's half our analysis. The other half is if T equals 1. And here, if Q equals 0, we want the next Q to be equal to 1, because if T is 1, Q should toggle each time the clock ticks. So if Q is 0, we want the next Q equal to 1. So we want D equal to 1. So if T is 1 and Q is 0, we want D to be set equal to 1. And if the current value of Q is 1, the clock should toggle after the next tick, so we want the next Q equal to 0. So we want D equal to 0. So if T is 1 and Q is 1, we want D to be equal to 0. So now what we have to do is we have to take our D flip-flop. It's got a clock, which we're just going to feed from outside. It's got a Q output. Our circuit that we're building is going to have some kind of T input. And by taking T and Q and feeding them into some sort of combinational logic, we want to generate this D input. And the behavior of this block of combinational logic is given by this truth table. And this can be, anything that we want, so long as it has this behavior. If T is 0 and Q is 0, D is 0. If Q is 0 and Q is 1, D is 1, and so on and so forth. And so you can sum of products this. And it's two min terms. And you can K-map it. And it's a checkerboard. And we've mentioned if you get checkerboard, start thinking about exclusive ORs. And if you look at an XOR truth table, you'll discover it looks exactly like this. And so D can be written more simply as just the XOR of T with Q. So if this block of combinational logic takes T and Q, XORs them, sends it out to D, you should be done. So your final circuit looks something like this. And that'll do it. So that's kind of a preamble to the stuff we started on Wednesday with this more complex state machine, which we're going to go back to. All right, and then question 5 was analyzing an SR. Negative edge triggered flip-flop, and you're given the table showing you how this device works. So a pair of zeros, the output is stable. The 1 on R resets, the 1 on S sets. And if you specify both set and reset, the reset takes precedent. So this is what we call reset dominant. And there's a start of a timing diagram here, and it just wants you to complete it. And so again, if I was drawing this and I meant for Q to be high, I'd put a little dotted line in the beginning so you can see it's at the top. It's drawn above the Q, so that kind of hints that it's a 1, but if you took this to be a 0 to begin with, that's okay. You get a different timing diagram, but I didn't take off points because it's ambiguous, right? But I think this was meant to begin as a 1, and so each time the clock drops, it's negative edge triggered. Each time the clock drops, we need to look at S and R and see what Q is. And so, I don't know, I can just write these in. There's a 0, 0. There's a 1, 1. There's a 0, 1. And another 1, 1. And a 1, 0. And a 1, 1. And a 0, 0. And a 1, 1. And a 1, 0. And I could, you know, based on this table, I could write down in here. We don't normally do this in timing diagrams, but, you know, for a homework question, I could write down from this table what should happen at each of these clock ticks. Well, this should just stay at Q. 1, 1 should be a 0. 0, 1 should be a 0. 1, 1 should be a 0. 1, 0 should be a 1. 1, 1 will be a 0. 0, 0 will stay at its current value. 1, 1 will go to a 0, and 1, 0 will go to a 1. And now I can just draw this in. So this should go low right here. And it should stay at a 0 until it gets over here. Now if you're showing propagation delays, this would rise a little bit after. If you didn't do that, if you did the transitions right on the clocks, that was fine. If I want you to take into account propagation delays, I would actually say in here, you know, show the effect of propagation delays. So that stays high until you get to this clock tick, and at that point it drops low. And that will stay low until this last clock tick, at which point it goes high. So something like that. That's a Q, not a 0. So if I was starting this off high, I would do that. If you decided Q was low right here, then this would just continue as low. Alright, so that was homework 4. Let's talk about lab 5. Well, let me mention homework 5. So homework 5 I'm not making due until a week from Wednesday. So you have your midterm coming up this Wednesday. You'll have lab 5 due Friday. And so I'm going to push the homework back so that it's a week from Wednesday, just for a tiny bit of a break from the craziness. So homework 5 due May 18th, and then it'll be a mad dash to the end. So this is not a homework from ENGR250.com. The homework is here, and it's a batch of questions related to state machine analysis. So I wrote this up last year. And a note on here, right? These problems take time. I'm serious about this. Doing one of these analysis problems can take you an hour if it's the first time you're doing it. It might take you 45 minutes for the second one. By the time you get to the end, you might be down to, you know, 20 minutes per problem. And these will not be on the midterm, but they will absolutely be on the final exam. And if you don't understand how to do them and you see it on the final, you'll probably have to skip that question. And it's usually, you know, worth a lot of points. Plus, it's going to be part of, you know, what we're doing the rest of this course. So you really want to spend time on the homework, which is part of why I'm giving you, you know, a week and a half from today to do this. And so it's a series of state machine analysis questions. And this first question says, you know, here's a machine that has an input X, an output Z, and a D flip-flop. And I'm asking you to analyze it, and I actually go through the steps in here of what that means. How do we analyze a state machine? So how many flip-flops are there? Given that, how many possible states are there? pick a name for each state. So this is echoing what we did on Wednesday, what we're going to do again today and also this Wednesday. And then write equations for the flip-flop inputs. Well, one flip-flop, one input D. So write an equation for D in terms of X and Q bar. And write an equation for the output Z, right, which looks like it's just equal to Q. So that's a straightforward equation. And then make a state transition table. That's where we left off on Wednesday. That's where we're going to pick up today. And then I gave you an example of the table here. And so you'll normally create this yourself. And then is it a mealy machine or a Moore machine? And then using this table and your answer to F, sketch the state transition table. Sketch the transition diagram. I'll have to fix that. Should be a diagram. And then question 2 is just a different machine. Do the analysis. Same for machine 3 and same for machine 4. And then 5 is a timing question. We'll talk about state machine timing later on today or Wednesday. But if you know what the propagation delays are in your combinational logic and what the setup and hold times are of your flip-flops, you can figure out what the maximum clock speed is. So that's a timing question. And let's see. Alright, so let me clarify that for questions 1 through 4. Your final answer is a state transition diagram. The state transition table is part of what you develop along the way, but it's the diagram at the end that is your final target. How many more homework assignments do we have left in this term? So this will be due week 7, so we'll probably have homeworks due week 8, 9, and 10. So after homework 5, 3 more. Alright, may as well talk about the midterm at this point, and then we'll jump into new material with Lab 5. So midterm exam will be Wednesday, 8 o'clock, right at the beginning of class. It's a 60-minute exam unless you have extended time accommodation. If you have an extended time accommodation, it's whatever, you know, an hour gets extended to based on your particular accommodation. So it begins at 8 o'clock. It will appear in Canvas right in here, so you'll need to refresh your Canvas page right around 8 o'clock. And there'll be a PDF that you download, which will have all of the questions. To submit your assignment, you basically write up your answers like you do your homework, turn them into a PDF, and upload that PDF. It's a closed book test. You're allowed 6 pages of double-sided notes or 12 single-sided pages, and you can do anything you want on those notes. You can mimeograph the entire textbook, you know, into little tiny squares and print that out. I don't recommend that though. But you know, good strategy for notes is as you're working on the homework questions, right? You're doing it somewhat from memory, from what we've done in lecture. But you're probably referring to your lecture notes, and when you're done with the homework, right, you've probably got an idea of what did I have to use to do these questions. So you've done a question with flip-flops, right? Do I remember flip-flops? I can't keep them straight, so put those down on your notes, right? And as you're working through the material, as you're working on the labs, as you're going back and working on, you know, the homework problems that weren't assigned or the problems in the book that are examples, right, be updating your notes so that by the time the exam comes, your current set of notes is just the stuff you need to help you do the problems we've been doing, right? As opposed to, you know, everything that you've ever written down, everything that I've ever said, everything that you found, right? Big stack of papers. That's not the note sheet you want to use for an exam, right? So as you're going through the material, as you're working on problems, you can be refining your notes, and by the time you get to the exam, you should have a few pages with the things that you know, can't quite remember completely, or that you get confused and so on. Just have those on your note sheet, and then you know, it's like doing homework questions. So 6 pages double-sided or 12 pages single-sided. I don't believe you need that many pages, right? This is meant to be more than you need, so it's not restrictive. But I don't want people to just come in with, you know, a stack of notes and the textbook and all of that stuff, because you'll spend your whole time flipping through pages. And an hour is not that long. Everybody's been uploading homework as PDFs, so presumably you have that process well worked out. But if you don't, if you have concerns about it, if it, you know, always takes you 5 tries, nail that down, right? If you need help, come to office tomorrow morning, and we can look at your tools, we can look at your setup, and I can help you try to figure out a really good way to take what you've written and turn it into a PDF. I don't know how many questions, several questions. And the questions will mostly be like homework questions or lab questions. So if you've understood the homework and the labs, you should be in good shape. I'm assuming that the work people are turning in for homework is your own work. And I'm basing, you know, my lectures and the exam on what I'm seeing on homework. And, you know, if everybody nails a question, good, people understand this concept, I'll go ahead and put a question for that on the exam. And my goal with the exam is just for you to demonstrate, you know, this understanding. And my hope is that, you know, everybody gets an A. That's what I would really love, right, from an exam. So I'm not trying to trip people up. I'm not trying to find the one thing that you didn't get, you know, that I mentioned for 5 seconds 6 weeks ago, right? I'm looking for generally the large overarching themes and the things that you've done again and again in homework and in working on the labs. So best way to study, go through the homework questions, go through the labs, make sure you understand everything that was done in the labs. Make sure you feel confident about your homework questions. Remember, I don't grade every homework question. So if there's stuff you're unsure about, ask about that. And you should be fine. So exam will go from 8 to 9. We'll do a break at 9 for 5 minutes, and then we'll come back and we'll lecture until the usual 9:50. There will be no tinkercad on the exam, so you won't be creating anything there. This will all be stuff that you'll basically write up by hand on paper. I recommend people come into Canvas during the exam only because inevitably, you know, there's a typo somewhere. I said, you know, write an equation for F, and there's no F anywhere in the circuit, and I meant Z. And, you know, I can just sort of like mention in Zoom, hey, you know, this should be a Z instead of an F, right? So hop into Zoom during the exam. I'll keep my microphone quiet unless I need to say a clarification or something. But, you know, if you're not in Zoom, I have no way to give you that kind of information. Study guide would be everything we've done. So, and like I say, look at the homework questions, look at the labs. That's where the material will come from. And yes, we'll have class at 9:05. So we'll take a 5-minute break after the exam, and then we'll continue with lecture. If you have extended time, then you probably want to, you know, silence Zoom at 9:05, because we'll be lecturing and, you know, talking about stuff, and you don't want that distraction. And so if you're working with extended time, I suggest, you know, somewhere in the first hour, at least look at all the questions so that if there's something that's just not clear what I'm asking, you can ask for clarification before 9:05. But if something comes up after, I'll try to respond. Thanks. All right, and make sure you upload by the deadline, right? So in person, I would normally, walk around the room at 9 o'clock. I tell people, thank you, that time is up, in 5 minutes. I'd give people, a heads up, and then at 9 o'clock, I'd say, go ahead and turn in what you have, and we'd leave for a break. And if I leave the room and I haven't picked up your exam, it's a 0, right? So how do we work that for an online situation? So Canvas will record when it thinks you turned in your exam, and it's 10 points per minute penalty if it's late, right? So turn it in on time. You can upload multiple times, and I recommend maybe halfway through when you get to a good point, scan what you got so far, upload that. And if you're scanning and putting into a Word document or something, that's a nice cumulative process, right? You get another page, just paste it into your document, export as a PDF, upload. You should have that down to like a 30-second process maybe, right? So it's not taking a big chunk of your time. And just make sure you upload, like a minute before. So don't get caught time-wise. If you have an extended time allowance, Canvas will tell you your submission is late. Don't worry about it, right? Canvas doesn't know about that. I know about it. So just turn it in before, whatever the extended time is. So if I want you to show your work, I will say show your work. If I don't, then you don't have to. But for example, if I say, use a K-map to simplify the following equation, you got to show me the K-maps, right? If I just see the simplified equation and no K-maps, then you wouldn't get credit for it. So do what's reasonable there. And you can always ask, during the exam, I'll be on Zoom. You can send me a chat message and say, hey, for this question, it wants to know how many library books we can catalog with a 6-bit number. Do I have to show my work? Or to convert this number to binary, do I have to show my work? Or things like that, and I can respond to you in Zoom. And seriously, I don't expect any surprises during the exam, so a lot of it should seem pretty straightforward, like, oh, this is just like that question I did 3 weeks ago. That's on purpose, right? All right, any other questions? All right, let's look at your next lab. So lab 5 is sort of the first lab that gets into this sequential behavior. Bye, have a good day. All right, see ya.
Bye.
Lab 5 gets into circuitry that changes over time on its own, right? Not just in response to changes to inputs, but actually kind of like does its own thing. And so we're going to play with some new types of devices here, and the main device we're going to use is called a 555 timer. And 555s are weird. Now this is one of the most amazing chips ever created. It's one of the best-selling chips of all time. It sold for $1 when it came out, I believe, which was unheard of because chips were about 5 times that price. And people have found so many uses for this little 8-pin chip. There's contests that different places hold to see what kind of designs people come up with using this chip. You can buy T-shirts with pictures of the chips, internal circuitry on it. I mean, it's a cult kind of device, and it's really tricky to get it hooked up just right. And in tinkercad, it's a little easier than in a lab. In a lab, I've seen students struggle for 3 or 4 hours to get this first circuit hooked up, because it's very different from sort of the digital circuits that we've been using, the 7404, the 7408. This is what we call an analog device. It doesn't just generate a high or a low, although the way we're going to use it is as if it were a digital device. But it's a much more general purpose chip, and it's basically set up to be a timer and an oscillator. And so the way we're going to do this is to turn this chip into a clock generator, something that outputs a pair of pulses, high and low, high and low, high and low, with certain timing characteristics. So so here's what the chip looks like. 8 pins. Ground is on pin 1. Power is on pin 8. That's different, right? Normally ground and power are on diagonals. That's not the case here. So ground pin 1, power pin 8. And then here's the way that we're going to wire this chip up. And there's lots of wires here. So we've got to use care when we build this. And in tinkercad, so let me make a general tinkercad comment. Let me grab a protoboard. So here's a physical protoboard, and when we want to wire a chip into a circuit, right, we usually take the chip and we put it like right in the middle. These aren't chips, they're buttons obviously, but same idea. We put the chip in the middle so that its pins sit on either side of this middle canal, and then if we want to connect to this pin right here, for example, we could put a wire in any of these 4 remaining holes. And now this wire is connected to that pin of the chip, and we can plug it into another hole, and so on and so forth. And that's the way that we normally use these protoboards. And the video that I referenced in the beginning of the course for a quick guide to prototyping goes through those kinds of steps. So 2 things that people have discovered you can do with tinkercad. One is, you can have the chip just kind of sitting over here, and you can take a line and you can just drop it right there on a pin and make a connection. And that works, but if you're in person for 270 in the summer, and if your class is doing, in-person labs, that's not going to work, right? The whole idea of the protoboard is that if you have a chip, right, it's just got this metal leg coming off of it. How do you connect a wire to it? Well, you could solder it, or you could try to wrap it around the pin, right? But those aren't really good solutions. So you put the chip in the board, and then if there's a leg sitting in this hole right here, I can plop a wire into any of these other holes. The other thing I've noticed people doing is they will take 2 or 3 or 5 or 6 wires and put them all in the same hole that the pin of the chip happens to go into. And that also works great in tinkercad. It works terribly on an actual protoboard because you end up breaking the protoboard. So 1 wire per hole at the most, which means if I have a pin of a chip, like here's, you can't see them, but there's pins underneath here. I've got a pin going into this bank of holes. If I want a wire connected to it, take your wire, put it somewhere in that same column of holes. So for Lab 5, this is a good place to change habits, right? Because one of the problems is if you have multiple wires jammed together in the same hole, or you have stuff sitting on the side of your design with just wires going to it, it makes it harder to trace what you've done, right? So if you only make connections between holes and columns, it's usually less cluttered visually to see what's going on. And all of that I mention mainly because this particular circuit is kind of a beast to get just right. And so you'd like to print this out or draw it on paper or something. And this is a good one to kind of go over with a highlighter as you place these wires. So how does this get wired up? Well, pin 1 gets connected to ground. Pin 8 gets connected to VCC. Those are easy, 5 volts. Pin 8, we also have this thing called a capacitor. So it's a tiny little device. On Tinkercad, you just grab a capacitor, and it's 0.01 microfarads. And the capacitor goes between power and ground. It's not a wire. It does not make a direct connection between this point and this point. And so we put this capacitor between VCC and ground, and it helps condition the behavior of the circuit. Now in Tinkercad, if you leave this off, things will still work. In a physical system, if you leave this off, things might work for a while and then they might suddenly stop working. So put a small capacitor between VCC and ground. VCC also goes directly to pin 4. And don't invert it. This circle is part of the diagram. But pin 4 goes straight to VCC. Pin 4 goes through a resistor RA to pin 7. 7 goes through another resistor RB to pin 2. Pin 2 and 6 get shorted together, and pin 2 goes through a capacitor C to ground. Pin 3 is your output, and you can put a 1K between pin 3 and pin 8. So lots of wires, lots of resistors, a few capacitors. When you build this circuit, what it does is oscillate. And the speed at which it oscillates depends on the values of the two resistors and the capacitor. So it oscillates in the sense that it goes high for a little bit, and then it goes low, and then it goes back to high and low, and it goes back and forth. The amount of time it's high is given by this formula. So 0.693 times RA plus RB times C. And RA, RB, these are going to be mega ohms. C is going to be microfarads. So this is a million ohms. This is a millionth of a farad. So those multipliers are going to tend to cancel. Million and micro will cancel each other out. And this time is in seconds. So you can plug in the values of mega ohm and microfarads for the resistors and capacitors and figure out how long this pulse should be high and how long it should be low. And it'll be, you know, on the order of seconds. It'll be something that you can watch, and with a watch or a clock you can kind of time out, you know, maybe count 10 pulses and see how long it took, and then divide by 10. So it's a human speed circuit. So what do we do for experiment 1? Let's see, you're going to talk about a compositor. I'm not sure what a compositor is. Are you talking video? I'm not sure, so I'm guessing the answer is no. Alright, so experiment 1. Implement the following design, that's this, to generate a clock signal. The clock generator will be used later, so keep it set up, right? Don't rip the wires out when you're done. Calculate and draw the clock signal based on the formulas provided. So using these formulas for these values, sketch a timing diagram for what you expect the output on pin 3 to look like. Alright. Compare the clock signal waveform observed with the calculated waveform and explain any differences. Now this is more interesting with a physical circuit because it's not an ideal device. It's a real world device. And you would see some pretty major differences. In Tinkercad is a simulation, so your output waveform is probably going to look very much like your calculated waveform. And so you can try to use the oscilloscope and change, you know, the settings, the horizontal period and the vertical scale, and try to see if you can get Tinkercad to reproduce the waveform that you drew that you expect to see. All right. So what do you need in here to get full credit for experiment 1? You need to talk about what you're doing. You need to have a circuit diagram. You can copy and paste, but put a note in there, you know, taken from Lab 5, ENGR250. And then you need to show your calculations for what time high and time low are, and then you need a drawing that shows that waveform. And when you're trying to show a waveform, you can't just do that, right? That tells you that the output's going to be low for some period of time, and then at some point it's going to go high. But, you know, maybe this is 50 million years, and then all of a sudden the output goes high. Or maybe this is, you know, a nanosecond. So to show a waveform, typically you want to show a repetition of pulses. And then, you know, show how long this is, and show how long this is, or show how long that is. But you want enough information so that somebody else doing the same experiment can look at their waveform and say, hey, my waveform matches. Or, oh, my waveform is completely different. All right, and then experiment 2, you're going to use this along with a 7493 to make a counter. And your counter is going to count from 0 to 9 and then go back to 0. And additionally, you're going to take the output of this counter, which is, you know, generating from binary 0 to 9, and you're going to use that to drive a 7-segment display. Well, how are you going to do that? Probably with a 4511, the thing that you used in your adder lab, Lab 4. So there's almost no detail here, but you're going to have several pages in your lab report describing experiment 2, right? So you know, you're going to say in this experiment, blah, 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 here's what I'm doing, right? System diagram. Well, there's not really an input to this circuit because, you know, you're driving this from a 555, so your system diagram may just be an output, right? Or it may be, you know, 7 outputs going to the 7-segment display. And then a detailed schematic, which means, you know, you need to show this part of your circuit. Don't just say, I use the circuit shown above, right? Draw a schematic diagram for experiment 2. So you're going to have this circuit. You're going to have values for these components. And this output is probably going to go into a 7493. And we'll look at that in a minute. And then the output of the 7493 will probably go to a 4511. And the output of the 4511 will go to a 7-segment display. So you're going to have lots of details in your schematic diagram. And then show a timing diagram. And what should the timing diagram show? Well, for the timing diagram, I'd like to see the output of the clock, and I'd like to see the 4 bits coming out of your counter. You don't need a timing diagram for the segments to the 7-segment display, and so on, but show me the output of the counter, and show me the 4 bits coming out of your, the output of the timer, and show me the 4 bits coming out of your counter. And then a test plan. So how are you going to know if your circuit works correctly or not? Well, it's probably going to be a matter of, you know, staring at it, waiting till it gets to 0, making sure it counts up to 9 and then goes back to 0. But, you know, write that out. And then go ahead, build it in tinkercad and test it. And don't forget to mention in your lab report what happened when you tested it. Did it work? Did it work well? Did it not work? And so on. Alright, then all the boilerplate stuff. Alright, questions about that other than 7493? Alright, so let's talk about the 7493. So we've glanced at this briefly. So you can find it on engrcs.com, go to component specifications, and 74LS93, which the lab tells you is pin compatible with the 74HS93, which is what tinkercad has. So, two devices in here. This is the 93, this is the 90. We're interested in the 93, so we're looking at this chip here on the right. And they mix these up throughout this data sheet, so make sure you're always looking at the right one. So 7493, oh, it's got all these inputs. Input B, R0, 1 and 2, no connection, no connection. 4 Q outputs, A, D, B, and C, and then another input A. And notice that this chip, ground goes on pin 10, power goes on pin 5, so this is another oddball, right? It's not the usual ground over here, VCC on the diagonal. They're in the middle of the chip. This happens, right? Why? Because it was the way that the layout ended up being when they designed this chip. So long as you know that, right, you can use this chip appropriately, but if you always put ground on 7 and power on pin 14, this isn't going to work. So ground up here, power down here. What does this chip do? You got to go down, you got to find a picture of it or a description or a timing diagram or something. So in this case, they're going to show you a block diagram of what's going on inside the chip, plus some tables. So LS93 count sequence. Counts from 0 to 15, Q, A, B, C, D, show your outputs. From 0, 0, 0, 0 up to 1, 1, 1, 1. Alright, pretty straightforward, but it says C note C. So what is note C? Output QA is connected to input B. So that's interesting. So QA is connected to input B. LS93, there's also a pair of reset inputs. If this reset is high and this reset is high, your output is all low. If either of these resets is low, then the output says count. So it acts like a counter. So these R inputs are active high resets. And if any of these goes to a logic 1, the whole counter resets to a 0. So that's good to know. Alright, so here's the picture of the 74 LS93. Input A drives the clock of this first flip-flop. Input B drives the clock of this second flip-flop, and the output of that feeds the clock of the third, and the output of that feeds the clock of the fourth. And there's your pair of reset inputs. And if they're both high, then the output of this NAND gate is a 0, and it goes into this bottom inverted input of the flip-flop. This is presumably an active low reset line. So if both of these are high, the output here is 0. That resets all of these flip-flops. Your count goes to 0. Alright. Got a couple of options here. Actually, you only have one option here. You have to count from 0 up to 9 and then back to 0. So here's what 0 looks like. Here's what 9 looks like. When you get to 10, you'd like to go back to 0, 0. Because you want to count from 0 to 9 and then back to 0. So you're going to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then when you tick once more, you'd like to go back to all zeros. So you need a 4-bit counter. And as this chip is currently sitting, it's not actually a 4-bit counter. It's a 1-bit counter and a 3-bit counter in a single package. No, 0 through 9 and then back to 0, not back down. So 0 through 9, 0 through 9, 0 through 9. Alright, to make this chip work as a 4-bit counter, all you have to do is take QA, connect it to input B. It's one wire. As soon as you do that, you've got a 4-bit counter. This is your clock, these are your outputs. If you don't do that, you can spend hours trying to figure out how to make this thing work for want of one wire from QA to input B. That's note C up here, right? Note C, output QA is connected to input B. That's what's going on. That's how you get a 4-bit output from this device. So just take a wire from pin 12, run it to pin 1. You're done. It's a 4-bit counter. So now your clock goes into pin 14 and your output comes on pins 12, 9, 8, and 11. Alright, so that's the first thing. Connect QA to input B. Second thing, feed your clock that's going to drive the count into pin 14, input A. So what's driving this? The output of your 555. So take pin 3 from your 555, run that into here. And now you've got a 4-bit output, Q, A, B, C, and D. If you run those into the 4 bits of input on the 4511, connect your 4511 to the 7 segment, this will count 0 through 9. But then when it gets through 10, 11, 12, 13, 14, 15, the display will be blank. So it'll go blank for a few seconds after 9, and then it'll go back to 0 and count up through 9 again. If this count is 15 and it ticks one more time, it will roll back over to 0. So this table up here goes back to the beginning after one more tick. Alright, so now you got something that's doing most of what it's supposed to do, except it's got this big period in the middle where the display is blank. So the last thing you want to do is use one of these reset inputs. So take one of these and tie it high. And the other one, let's use this to reset the counter when it gets to 10. And the idea is to build a little piece of combinational logic. That takes in Q, A, B, C, and D and generates a reset signal. So that when Q, A, B, C, and D are equal to 1, 0, 1, 0, reset becomes a 1. And you feed that reset back into one of these reset inputs, or into both of them if you like. And what you can do is have this counter now act so that it counts from 0 through 9. And then on the next clock tick, it goes to 10. But that 10 sets the reset to be a 1, and it drives the count back to 0. So that's how you get to go from 0 to 9, and then back 0 through 9, and so on. So you do a reset when the count equals 1010. And there's a few ways to do that. You can get away with doing that without a whole lot of logic. Alright. Any other questions about that? This is another one of these things that, like, if you start putting chips on protoboards and sketch out some circuits and wire them together, it will start making a lot more sense than listening to someone talk about it. So one possible suggestion is, take this chip, throw some LEDs on Q, A, B, C, and D, take your function generator, generate a pulse every few seconds, and just feed that into input A, and see if you can make this thing count, driven by a pulse generator in tinkercad. Or put a push button on here and hook it up so it generates, a 1 or a 0 when you push it, and see if you can push through a counting sequence. And that lets you gets this thing figured out completely just by using LEDs. And once you know how to make this thing count, the rest of the lab is pretty straightforward, right? The rest of experiment 2 is pretty straightforward. You take these, you run them into a 4511, you run that to a 7 segment. You can do that with a push button too, and now, as you push the button, you can see it count up on the display, right? And then you can worry about this reset circuit. So come up with a way so that when the count gets to 10, it goes back to 0. And now you can, push button it up through 7, 8, 9, you push button it again, and it goes back to 0. And then if you've done experiment 1, it's just instead of having a push button go here, take the output of this 555, hook that up to input A. So this lab, you can definitely work your way up to the final experiments, right? Do them in pieces. And you can talk about that in your lab report too. I mean, that's all fair game, right? It's not required, but you can say, first I drove the input A, pin 14, from a push button, and here's what happened, and then I used a function generator and so on and so forth. Right? So keep in mind, labs are different from homework. Homework, here's a set of questions, write the answers down on paper, give it to your teacher, you're done. Lab reports are very, very different, right? They're describing and documenting a process you went through, a series of experiments and procedures and observations and conclusions and so on. And you're documenting all of that in a way that somebody else can look at it and understand what happened when you did this lab, and then they can try to do it themselves and get the same results or see different results. So it's kind of a totally different mentality. All right, cool. Let's do a 5-minute break. We'll come back and we'll pick up with the state machine analysis that we were starting on Monday. On last Wednesday, we'll work through that, and then we'll go through some other examples of state machine analysis. All right, so I'll see you back in 5 minutes. Alrighty. So, if you've got questions, this is the time to be asking them. I'm just going to keep going through stuff. All right. Well, let's continue with state machine analysis. So, we were playing with this kind of random circuit last week, and we started with this circuit, and we wanted to know how it behaved. And so we had a series of steps we were following. So the first thing was to see how many flip-flops we have, which is 2, and then decide how many states that corresponds to. And if we have 2 flip-flops, each of these can be a 0 or a 1, how many combinations of outputs can we have? Well, this could be a 0, 0, 0, 1, 1, 0, or 1, 1. It's 2 to the second, or 4 possible states. If we had 3 flip-flops, it would be 2 to the third, or 8 possible states. So the number of possible states is just 2 to however many flip-flops you have. And then we make a table that basically names each of these possible states. So the particular state of the system is just the combination of flip-flop outputs. And the state is based on the outputs, not the inputs. So Q1, Q0 could be 0, 0, 0, 1, 1, 0, or 1, 1. And I just chose to name these A, B, C, D, but we could name them anything we like. And I'm going to be very consistent. I'm going to number my flip-flops and my inputs and everything else starting from 0. And when I make tables, I'm going to use the more common convention of, putting the most significant bits as the ones with the higher subscript. So Q1, Q0, or Q2, Q1, Q0. Q2 would be most significant, as opposed to Q0, Q1, Q2, or, Q2, Q0, Q1. None of these would be incorrect, right? But humans have historically been a successful species because of our ability to form habits, right? And this is a habit, right? Every time that I write down a sequence of things with subscripts, I put the larger subscripts on the left. And that's a habit most people doing this kind of analysis would follow. But, develop a habit that is consistent for you, and it saves you time and energy when you're going through this analysis, or, next week, this synthesis process. So I'm going to do Q1, Q0. I'm going to call these A, B, C, D. The next step was to write equations for the inputs of the flip-flops and for the output of the circuit. And so remember, this whole thing inside here is one circuit. It's got a clock feeding in, and the clock is always oscillating. And this has an external input X and an external output Z. And the idea was, let's figure out what this does over time based on the input X. Alright, so to determine how these flip-flops change over time, we have to write equations for their inputs, because whatever type of flip-flop this is, the only way we know what it does in response to a clock tick is by understanding its inputs. If it's a JK, we have to know what J and K are. In this case, it's a D flip-flop, so we have to know what the D input is. So we write the D inputs in terms of flip-flop outputs, either the Qs or the Q bars, and if there's external inputs, those external inputs. So this is an exercise in sort of analyzing the schematic. And so D0, well, that just comes from Q0 bar, so that's this first equation. D1 comes out of an OR gate. One input is X. The other input comes out of an AND gate. And the two inputs to the AND gate are Q1 and Q0 bar. So there's an equation for D1. And then Z comes out of an OR gate. One input is Q1 bar, and the other input is Q0. state machine analysis is definitely an exercise in showing all your work. Because if I, forget this bar up here, my answer is going to be completely wrong. And if all you turn in is that final state diagram and it's wrong, it's 0, right? Whereas, if you forget a bar up here, hey, you traced this wire and you thought it came there instead of there, that's not a big deal. That's like a point, And if everything else comes out correct, you probably get most of the credit for the question. So, all these things we're doing, all these things we're saying, you want to include that in your work on homework questions and on the final exam. All right, so now we've got our equations. We can kind of forget about the schematic. We've taken all the essential information from here, captured it in these equations and this state table. So now we make sort of the main piece of this exercise, which is a state transition table. And this will completely describe how the machine behaves over time. So, table looks like this. We have present state. And we have our input. And we have output. And we have next state. And a lot of space inside here. Alright, so our present state is either A, B, C, or D. We have one input, X, it's either a 0 or a 1. So we have 4 states and 1 input. And our state is just, what's the current value of Q1 and Q0. So I'm going to put some subheadings under here. I'm going to list a name. And I'm going to list Q1 and Q0. And my input is just going to be X. And my output is just going to be Z. And let's just worry about this part for now. So it could be that I'm in state A, which means my inputs are what? My flip-flops are 0, 0. Could be I'm in state A and my current input is a 0. Or I could be in state A and my input X could be a 1. Or maybe I'm in state B, which means my flip-flops are a 0, 1, and my input is a 0. Or maybe I'm in state B, and my input is a 1. And you're probably seeing a pattern. So my state transition table is going to have 8 rows to it. It's 8 rows because I have 4 possible states and 2 possible inputs. So this, I'm just filling in based on how many states do I have, how many inputs. I haven't done anything with my equations yet. But these are basically, the inputs to the state machine in some sense. Now we don't list the clock. So the clock is never an input in the sense of showing up in this table. The clock is always there running in the background. What we're going to do is we're going to say, hey, if we're in state A and my input is a 1, what is my output? And after the clock ticks, what is my next state? And that's our goal, is to say, given a present state and an input, what's the output? And after the clock ticks, what's the next state? So the way to think of it is your present state plus the input tells you what the output is and what the new state's going to be. That's what we're trying to figure out here. Because that's our ultimate goal is, hey, how does this machine change from state to state each time the clock ticks, and how does the output change? So you got to understand that before doing anything else on here. And once you understand that, the rest of this is pretty mechanical. So here's what drives our state transition table. All the possible combinations of present state and input. So present state is either A, B, C, or D. Input is either 0 or 1. 8 possible combinations. Alright, now I can go ahead and I can write in my output from this equation. Z equals Q1 bar or Q0. Well, I would suggest you make a column for Q1 bar and then do the OR. Let's go ahead and do that. Let's make a column for Q1 bar. Q1 bar is just the complement of Q1, so these are all zeros, this will be all ones. And here Q1 is all ones, so Q1 bar will be zeros. And I'll put my output here. So here's the output Z, and Z is just an OR. It's an OR of Q1 bar with Q0. So it's this column ORed with that column. So anywhere that Q1 is a 1, our output's going to be a 1. I really want a third row there. And if Q1 bar is a 0, but Q0 is a 1, which is these two rows down here, our output will be a 1, otherwise the output's a 0. Alright, so we've got our output done. Just screenshotting attendance. Alright, so now we want to know what the next state is ultimately, which means what are the new values of Q1 and Q0. Well, the only way we can know that is if we know what the inputs to the flip-flops are. So we need to write down an input for D1 and for D0. And once we know that, we can use our understanding of D flip-flops to say, hey, what's the new value of Q1 and Q0? Alright, so we need to figure out what D1 is. Well, we're going to have to do a Q0 bar ANDed with Q1 or X. So let's go ahead and put a column in for Q0 bar. I know you can do this in your head, but let's just be super kind of methodical about it. So Q0 bar is the complement of Q0. And then D1 is X ORed with Q0 bar ANDed with Q1. So if X is a 1, D1 should be a 1. So D1's going to be 1 here, 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 and here. If X is a 0, then D1 will be 1 if Q1 is a 1 and Q0 bar is a 1. So let's take the AND of Q1, which is this column on the left, and Q0 bar, which is this column we just drew. So this leftmost column and this rightmost column, let's AND those. Well, here's a 0 and a 0, so those ANDs are 0. Here's a 1 and a 1, so that ANDs to a 1. And here's a 1 and a 0, that ANDs to 0. So do whatever your approach is to filling in a value based on an equation. And then D0 is pretty straightforward. It's just the complement of Q0. Well, we've got a Q0 bar. So D0 is just Q0 bar. So this is just 1, 1, 0, 0, 1, 1, 0, 0. Okay, this is very mechanical. I'm not looking at this and thinking this is a 1 and this is a 3, what does this mean? This is a 2, what does this mean? We're just methodically going through and we're trying to say, hey, if this is my present state A and my input is a 1, then D1 and D0 are both 1s. We're not saying anything about what that means, about why that is, about the implications of it. We're just filling out a table. And eventually, pretty soon, we're going to interpret all of this and say something about the machine as a whole. But for now, we're just filling in, what are the flip-flop inputs in each of these 8 possible combinations. All right, here comes the good stuff. I'm going to have columns labeled Q1 plus and Q0 plus. Q1 plus is saying, hey, if my D input is a 0, what will the value of Q be after the clock tick? So this next state is, after your clock goes through whatever its edge is, its positive edge or its negative edge. And with a D flip-flop, all we have to know is what the D input is. Whatever the D input is, that tells us what the new value of Q will be. So for D flip-flops, we can just copy this column into here. But we're not just copying because that's what we do, right? We're copying because for a D flip-flop, if the D input is 0, the clock ticks, the output will be 0. If the D input is 1 and the clock ticks, the output will be a 1. So the effect of that reasoning is we can just copy this column into here. But it's not because we just copy columns when we do a state transition table. It's because we're saying if the D input to flip-flop 0 is a 1, then when the clock ticks, the Q output of flip-flop 0 will become a 1. And if the D input is a 0, then when the clock ticks, the output will be a 0. Alright, so now we're almost done. We've said, hey, given this circuit, if these two flip-flops happen to both be 0s, and our input X is 0, and the clock ticks, this flip-flop will output a 0, and this flip-flop will output a 1. Well, if Q1 is a 0 and Q0 is a 1, that's what we call state B. If both flip-flops are outputting a 1, that's what we call state D. And so now we can go through our state table and we can write down the names of each of these states. And there's your complete state transition table. This is everything we need to know about the circuit. The whole takeaway from this is how we get this. And so we started with a circuit diagram. We went through all of these steps, some of them on Wednesday, some of them just now, and we ended up with this table. Well, there's a lot of information in here, but what we care most about from this table is if you're in this state and you have this input, what's the output? And what's the next state? And everything else is just to help us fill in this last column. Well, tables are nice. They contain a lot of information, but they're not as visually meaningful to us as pictures or diagrams. So our last step in doing analysis of a state machine will be to take this table and turn it into a diagram. So a state transition diagram can be written as follows. So each state is going to be represented by a circle. And I'm going to name the states in here, A, B, C, D. And the way I do this, I could have written them all in a row. I could have done A, B, C, D. But when you're done, you may find that if you move these things around, your drawing is simpler. And so you may, do this on paper and try a few times and then come up with a nice, succinct way to draw this and make that be your final analysis. Now, there's this business of mealy versus Moore machines. And so in a Moore machine, the output only depends on the state. In a mealy machine, the output depends on the state and the input. And in this machine, by looking at the diagram, we can see the output only depends on the current state, Q0, Q1. If we look at the equation for the output, it only depends on the current state, Q0 and Q1. So this is a Moore machine. If we had an X or an X bar or something involving X going into some logic that generates Z, then the output would also depend on at least one of the inputs. That would be a mealy machine. Okay, if it's a Moore machine, all we need to know to say what the output is what is the current state. And so here we can see in state A, the output is 1. In state B, the output's 1. State C, the output is 0. State D, the output is 1. So for a Moore machine, when we make our diagram, we can list the outputs inside each of these state bubbles. And I'm going to make a key, just like on a map you have a key for what the different symbols mean. I'm going to make a key for my state transition diagram. And my key is going to say state. And then I'm going to say the thing underneath it is the value of Z. That's the output. We might have a circuit with several outputs. We might have a circuit with several inputs. So we're always going to have a key showing what these pictures mean. Alright, and then the last thing we do is we draw arrows to show how we move from one state to another. Well, if we're in state A, what is our next state going to be after the clock tick? It could be B or it could be D. Which is it going to be? It depends on the input X. So if we're in state A and our input is 0, our new state will be B. So for each of these states, we're going to draw an arrow. And on that arrow, we're going to list the value of our input X. So this is our key. So if we're in state A and our input is 0, we should go into state B. So I'm going to draw an arrow here. I'm going to put a 0 on it. And that's telling me if I'm in state A and my input is a 0, my input X is a 0, I'll go to state B. If I'm in state A and my input is 1, my new state is D. So from state A, if I have a 1 in X, I'll go to state D. And now we just fill in the other arrows from this table. If we're in state B and we have a 0 coming in, we go to state A. So we have an arrow in this direction. If we're in state B and our input is a 1, we go to C. So here, if we have a 1, we'll go to state C. If we're in state C and we have a 0, we'll go to D. If we're in state C and we have a 1, we'll go to D. So state C always goes to state D. So we have one arrow for when X is 0 and another arrow for when X is 1. And then finally, if we're in state D, we go back to either state A or state C, depending on the input X. So state D, if our input is a 0, we'll go back to state A. And state D, if our input's 1, we'll go to state C. So that looks like this. And we're done. So this diagram captures all of the information about this circuit and all of this analysis that we've done. And so what does this machine do? Suppose it begins in state A. If you set your input to 0 and you tick the clock, you're going to bounce between state A and state B, state A, state B, state A, state B. You're just going to ping back and forth between those, and your output's going to stay at a 1. If at some point you're in, say, state B and you change your input X to a 1, the next clock tick you're going to go to state C and your output's going to drop to a 0. And then at that point, your next clock tick, regardless of the value of X, is going to take you to state D, and your output will be a 1. And then on your next clock tick, depending on your input X, you're either going to go back to the beginning to state A, or you're going to come back to where you just were, which is state C. And once you're in state A, if your input is 1, you're going to go immediately to state D. Your output will stay 1. And then, based on your value of X for the next clock tick, you'll either go back to C with an output of 0, or you'll ping back to A with an output of 1. So this is kind of a random circuit. It doesn't have a direct, obvious behavior to it, like it doesn't just go from A to B to C to D and so on. But whatever the circuit does, right, by going through these steps, figuring out the number of states, naming them, writing equations, making your state transition diagram, deciding if it's a mealy or a Moore machine, and then drawing your circuit diagram, you get this easier analysis of your circuit that shows you how it moves from state to state based on the inputs going into the system. And so each time the clock ticks, it'll follow one of these transition arrows to a new state, and in that state it'll have some output. All right.
I know you
Go ahead.
I know you probably already went over this, but why are we have it A over 1, C over 0, state over Z?
So we are trying to display multiple pieces of information in here. So the main two pieces of information we want to know are what state are we in and what's the output from the system. And so in this table, right, we can see, for example, if you're in state B and your input is a 0, your output will be a 1 and your next state will be A. So the way we capture that information is we say if you're in state B and your input is a 1, right, the arrow shows us, hey, your new state's going to be C. But the output does not depend on your input. It only depends on your present state. So we can show the output just based on what state you're in, and we do that by just drawing it inside the circle. So we have the name of the state up here, and then the output value for that state below it. And we're just drawing a line to separate those. I'm going to say always draw a separate arrow, because if we start putting in commas here, it's going to confuse things. So even though, both inputs 0 and 1 take you from C to D, go ahead and do 2 arrows. And that's going to come up when we have a Moore machine, sorry, a mealy machine. And with a mealy machine, we might have a current state. And the output, so we have our input X, but the output will depend not just on what state you're in, but also on what the input is. So for a mealy machine, we usually list the outputs on the arrows, not on the state. Because if you're in a given state, it might be that if X is 0, you have one output. If X is 1, you have a different output. And so for mealy machines, we list the outputs on the transition arrows, and so we put a slash in between them. And that's where a comma can get confusing, so separate arrows are better. And you might have, some outputs that are mealy outputs and some that are more. So the more outputs we could list under the state inside the bubble, and the mealy outputs we can list on the transitions. And so if you had a machine with say 3 inputs and maybe 2 outputs, and Z1 was a more output and Z2 was a mealy output, then your state diagram might look like this. You'd have the state, you could list the more output here, and then on your transitions you'd list your inputs, so X3, X2, X1, and then a slash, and then we could list our mealy output, Z2. I should have started from 0 to be consistent, but But the process of getting to this is always the same, right? So follow those steps, decide how many states you have, name the states, write equations for your flip-flop inputs and for your outputs, make a state transition table which shows for each input and state combination what are the outputs, find the values to the inputs of the flip-flops, use what you know about flip-flops to find the next state of the outputs of the flip-flops, write down the state name corresponding to that, and then turn it into a diagram. We're obviously going to go through more examples of this on Wednesday. But that's the basic process, and there's examples in the textbook that go through this in a few different cases. And this changes in a few ways. So depending on the type of flip-flops you have, how you go from here to here is going to be different. So suppose we do exactly the same thing, but we say these are toggle flip-flops. So now my equations are, T0 equals Q0 bar. T1 equals all of this stuff. And so these are toggle flip-flops. Well, now all of this is potentially changed. But what does a toggle flip-flop do? Right? It says if your T input is 0, your new value of Q is the same as the old. If your T input is 1, the new value is the opposite of your old. All right, so let's just look at flip-flop 1, T1 and Q1 plus. If T is a 0, your flip-flop does not change value. So what's the current value of Q1? It's a 0. That's the new value. Here T1 is a 1, which says the flip-flop will toggle. The current value is 0. The new value is going to be 1. Same thing here. It's going to preserve and it's going to toggle. Here it's going to toggle, so this is going to change from a 1 to a 0. This is going to toggle from a 1 to a 0. This will not change, so it was a 1, it'll stay a 1, and this is going to toggle from a 1 to a 0. And then Q0 does the same thing. If T is a 1, your flip-flop will change value. So here your flip-flop was in a 0, the output will now be 1. Here the flip-flop will be unchanged, so that'll stay as a 1. Here it will toggle, so it'll go from 0s to 1s, and here it will stay the same, so it'll be 1s. So it looks like Q0 bar is always 1. And so we can write down the state names. This is B and D and B and D and B, B, D, B. So this would be a different kind of state diagram. right? It looks like whatever state you start in, you end up in either state B or D. And if you're in state B, you can go to either B or D. If you're in state D, you can go to either D or B. So this would be a machine that would have some kind of you know, funny business going on in the beginning if you're in state A or C, and then it would settle down into this very systematic behavior where it basically pings between B and D based on the value of your X input. And in state B and D, your outputs are always 1, so once you get through this initial period, your output's always going to be 1. So you got to understand what type of flip-flop you have, how its output changes in response to its input, and that's how you fill in these columns. If you start in state A and your input is a 0, your next state will be B. If you start in state A and your input is 1, your next state will be D. So you'll definitely get to state B or D after 1 clock tick. Same thing if you start in state C. Whatever your input is, your next state's going to be B. And so, you know, if you said the system will begin in state A, that would be some initialization maybe that's taking place, and then it goes into this regular ping pong behavior. All right, so think about that. Go through the examples in the book. Take a stab at the homework questions. We'll do more examples of this on Wednesday after the midterm, and we'll also talk about state machine timing, which is question 5 on the homework. That's a really simple analysis. That'll take us like 5 minutes to get through. But this should be enough for you to get started on state machines. State machines are not on the midterm, right? Everything up through flip-flops could be, but the stuff we're doing today will not be. So midterm, let me see something. Hold on one sec. I'm thinking I will not put flip-flops on the midterm. Alright, so midterm will be everything up to, but not including flip-flops. So all the combinational stuff, all of the product of sum of products, everything that we did, until we started talking about sequential circuits with memory. So it'll be everything before flip-flops. Alright, but we'll pick all this stuff up on the final. Alright, that's all I got. Have a good one. I'll see you in office tomorrow if you want to come in for questions. Otherwise, I'll see you on Wednesday. Alright, thanks.